культур до харчової промисловості. Хочу коротко розповісти про нас, АЛТ Україну, і також про Oxford Instruments, які є виробником цього обладнання. Починаємо. Так. Отже, тему я вже назвала. Поговоримо сьогодні ми саме про ЯМР-аналізатори MQC+. І, отже, про компанію АЛТ Україна. Ми розкриваємо потенціал новітніх технологій для здоров'я та безпеки нації. Це наша візія. Ми є одним із найбільших постачальників сучасних комплексних рішень для лабораторій різних спеціалізацій і закладів охорони здоров'я. В нашому асортименті є обладнання та витратні матеріали. Ми повністю проводимо сервісне обслуговування і підтримуємо з методиками користувачів на протязі всього терміну служби обладнання і реалізуємо великий загальнонаціональний проєкт. Ми є на ринку з 2008 року, забезпечуємо повним супроводом від підбору рішення до його впровадження і подальшого обслуговування. Також наша система менеджменту сертифікована відповідно до ISO 9001. Маємо спеціалістів топ-класу, які постійно проходять різні програми розвитку і підвищення кваліфікації. Також у нас розвинена інфраструктура, маємо власну логістичну службу та склади. Трохи про компанію Oxford Instruments, виробника обладнання. Oxford Instruments Magnetic Resonance – це підрозділ компанії глобальної Oxford Instruments, яка спеціалізується саме на розробці настільних ЯМР-спектрометрів і аналізаторів для наукових досліджень і промислового контролю якості. Oxford Instruments є одним із світових лідерів у сфері магнітно-резонансних технологій. Рішення компанії використовуються у різноманітних сферах, таких як фармацевтика, полімери, харчова галузь, агропромисловість, хімія і нафтовидобування. Oxford Instruments та АЛТ Україна почали співпрацювати з 2008 року. Які ж є рішення, саме ЯМР-рішення у Oxford Instruments? Це є дослідницькі ЯМР-аналізатори MQC-R, ЯМР-аналізатори MQC+, про які ми будемо сьогодні говорити, а також настільні ЯМР-системи X-Pulse та X-Pulse 90. Які теми ми сьогодні будемо обговорювати? Саме це буде застосування ЯМР-аналізаторів взагалі в харчовій промисловості. Серед тем буде олійність і вологість в насінні олійних культур, визначення загального твердого жиру в продуктах харчування, таких як, наприклад, маргарин, розподіл розмірів крапель води в харчових емульсіях, визначення вмісту олії та жиру в снеках, шоколаді, кормах для тварин та інших зразках. Ну і також визначення ФОГ в стічних водах, тобто мається на увазі загальний вміст жирів, масел, олій і мастил у воді. Також, що хотіла сказати, важливе, що ЯМР-аналізатор MQC+, відповідає також державним стандартам України, а саме ДСТУ ISO 10565 для насіння олійних культур, ДСТУ ISO 10632 для продуктів переробки насіння олійних культур, а також стандарту ДСТУ ISO 8292, який стосується визначення вмісту твердих жирів у харчових маслах і жирах прямим методом. Це моя була коротка презентація для того, щоб розповісти коротко, про що ми будемо сьогодні говорити, познайомити вас з компаніями. Дякую вам за увагу. Також пропоную за QR-кодами підписувати на наш телеграм-канал, LinkedIn, Facebook та YouTube. Сьогодні нашим спікером буде Кевін Нот. Це фахівець з продукту Oxford Instruments. Він нам буде проводити вебінар, основну частину, а також у кінці в нас буде сесія питання-відповідь. Ви можете свої питання писати зараз протягом вебінару в чат, можете на кінці вебінару, і я все це буду перекладати з української на англійську і навпаки. Тож зараз надаю слово Kevin. Kevin, please, you can say hello, short introduction of yourself. Sorry, we can hear you.
Yes, my name's Kevin Knott. I've been at Oxford Instruments for over 20 years now. So originally applications scientist, and more recently the product manager for the MQC Plus analyzer and the MQCR research system.
Окей, thank you. Отже, Кевін сказав, що працює вже в Оксфорді більше 20 років, і наразі він є як методистом і продакт-менеджером саме з лінійки MQC Plus для мер-аналізаторів. Отже, переходимо до основної частини. Okay, thank you, Kevin. Now we will start our main part.
Okay. Hello, I'm Kevin Knott, the product manager for the MQC Plus and MQCR time domain instruments. I would like to welcome everyone to my webinar on oil and fat analysis, in which I will describe what time domain NMR is, what it can measure, and how it can be used in the food chain, from oilseeds through to food manufacturing. I'm going to start with agriculture and raw materials. The primary reason for growing oilseeds is for their edible oil, which is used for foods and other applications. Higher yield crops can command a greater price, hence it is important to accurately measure both the oil and water content which affect this. Measurement of oil content is also important for seed breeding to produce the best crops. There are a variety of reasons to use NMR over other methods. For example, where ISO standard methods need to be followed, where accuracy and reliability of the measurement is important for determining crop value when trading oilseeds, where high throughput is required for testing laboratories, either for manual measurement or using automation for measurement of smaller research quantities, when new seed varieties that have been bred need to be measured, for measuring sunflower seeds, where NMR is generally accepted to be the most reliable method, and finally for measuring oilseeds prior to and their residues after crushing and solvent extraction for optimizing seed oil yield. Measurement of oil and water content is based on separation of the signals from the solid matrix, water and oil. The sample is measured by applying radiofrequency pulses on a sample inside the static magnetic field. The signal immediately after the first radiofrequency pulse represents the total signal from the sample. Thereafter, the solid signal decays to zero, leaving the cumulative signal from both the oil and water. The timing of the second pulse, as specified by the ISO method, is applied to separate the oil from that of the water, which is considered to be bound to the seed matrix below a concentration of 10%. The water signal is derived from the difference between the signal after the solid has decayed and the peak of the echo, which represents the signal from the oil. There are some exceptions, but in general, time domain NMR requires calibration against samples measured by a primary reference method. In principle, given the calibration is linear, only 2 or 3 samples are required to produce the curve. However, it is recommended to measure at least 6 samples that span the concentration range of interest, due to errors inherent to the reference method. For oil content measurements, we would measure the signals at the peak of each echo. Then it is often necessary to divide or reference each NMR signal by the mass, since the instrument does not know how much sample is being analysed. These NMR values are then plotted against their concentrations to produce a calibration. For each reference sample, we take one subsample that we oven dry to obtain a reference value for water content. We then use salt salt extraction on the same sample to obtain a reference value for oil content. We then take another subsample for TDNMR analysis and use the predetermined reference values for the calibrations. We also need to make sure that the reference samples span a reasonable concentration range. However, given the calibration is linear, you can analyze samples outside of this range. In this example, you can see that it's possible to obtain approximately 0.1% standard deviation between the calibration and reference values, which is a measure of the accuracy of the TDNMR method. The primary reason for growing oil seeds is to produce the edible oil. However, the residues or byproducts are often used for food ingredients and animal feed. Here are two different studies which show that seemingly different byproducts can be measured using the same calibration, and that they can be measured either ground or whole. Furthermore, you can use the seed and byproducts in the same calibration. Thus, the calibration may span across a very wide concentration range. Lastly, that TDNMR may be calibrated against different methods. Both studies used reference values obtained from salt salt extraction. However, the reference values used for the calibration on the right were obtained after acid hydrolysis, which breaks down the matrix prior to extraction. As I mentioned earlier, TDNMR can distinguish solids from liquids. As a consequence, it is also possible to measure solid fat content at different temperatures, which relates to the melting properties of the edible oil or fat. Aside from pure oils, fats, or blends, solid fat content is normally measured for both dairy and non-dairy spreads, such as butter and margarine, as well as fats used in the bakery and confectionery industries. This diagram shows both fast and slow decaying components, representing solid and liquid fats, respectively. The true solid fat content cannot be determined accurately at the start of the decay, so instead the signal loss during the dead time between the radio frequency pulse and the signal being recorded has to be determined or calibrated for using real samples with known values. However, normally a set of pre-calibrated glass-sealed standards are supplied with the instrument. Once the instrument has been calibrated, it is very easy to collect data on samples that have been equilibrated at different temperatures. However, each sample requires tempering beforehand. Firstly, to remove the thermal history. To do this, the sample is melted, then the temperature is dropped first to 60 degrees Celsius for 5 minutes, then 0 degrees Celsius for an hour. Finally, samples are conditioned at each measurement temperature. Either the same sample in series, or more commonly, multiple samples are prepared for each temperature to be measured in parallel to quicken the process. Thus, 5 samples measured at 4 temperatures will require 20 samples in total. Here are some examples of melting profiles, that is, the solid fat content of edible oils and fats conditioned at different temperatures. The melting profile relates to their sensory and physical properties, which is important for their eventual end use. The shortenings tend to have higher solid fat contents across a temperature range to ensure that the baked goods in which they are added are solid but not greasy at ambient temperatures. Whereas the margarine has lower solid fat content to ensure that it is soft and spreadable when it's removed from the fridge. TDNMR is internationally recognized for the measurement of solid fat, and there are AOCS, ISO, and IUPAC official methods for the direct method. Another important property of margarines and food emulsions in general is droplet size, which is also measurable using a different time domain NMR method. Traditionally, methods to measure droplet size are optically based. That makes it difficult to analyze opaque samples. Emulsions are unstable because the temperature is not regulated in a microscope, for example. And the measurement and data analysis can take hours, particularly since the data is typically analyzed manually by the operator. TDNMR measurement of droplet size is based on sensitizing the signal to diffusion using pulse field gradient hardware, highlighted in yellow. The advantages of the TDNMR method, which has been used for many years, are that the whole sample is measured non-destructively, not just on the surface. Emulsions can be stabilized at the desired temperature. Both measurement and data analysis are fast, typically taking minutes, which means that it can be used as a quality control measurement. Water droplet size distribution is an important property in margarines and spreads. Low-fat spreads tend to have a higher water content, and the water droplets must be small, less than 10 microns, to avoid microbiological deterioration. In this example of a droplet size distribution from a spread sample, the majority of the droplets are well below the 10 microns required for microbiological stability. As well as for QC, this measurement can also be used in R&D to re-optimize the formulation according to the latest trends or local legislation. In addition to solid fat content and droplet size, time domain NMR is widely used to measure oil and fat content of food ingredients and the manufactured end products. Time domain NMR has been used as a solvent-free method to measure oil and fat in foods for decades, because it was apparent early on that the measurement was independent of granularity, colour, and the other constituents. It is primarily used for quality control, but it is also used to help set up and monitor production lines for snack foods made from potato, corn, etc., nuts, chocolates and cocoa derivatives used in their manufacture, milk powder, infant and nutritional formula, food ingredients, for example, derived from seeds or grains, and dry animal, pet and fish feed, or as is without drying. Whereas foods with higher moisture content, including meat, fish, dairy, and many processed foods, must be dried beforehand. In some instances, it is possible to calibrate using the pure oil. This is especially true of processed foods, and particularly those which have high fat content. For example, a snack food can be calibrated using a sample of the pure oil which is used in the frying process. This graph shows points at 0 and 100% from the pure oil. In between, there are real data points from crisp or chip samples. The reference values were obtained using solvent extraction, preceded by acid hydrolysis for measurement of total oil content. The acid hydrolysis is used to disrupt the matrix in order to release all the oil. Thus, we can see that in this instance, the pure oil calibration can provide a measurement of total oil content. In contrast, the accuracy of Soxhlet alone may vary depending on the matrix type, where some of the oil remains unextracted. In terms of sample preparation and measurement, snack food is typical of most food applications. First, the samples are broken up and homogenized to obtain a representative sample. Particle size is not an issue. Then the sample is inserted into pre-tared vial using the packing tool. The vial is then reweighed to obtain the sample mass. The sample is then conditioned at 40 degrees Celsius for 20 minutes to ensure all the oil is mobile. Some samples may require higher temperatures, for example those containing palm oil, to ensure all the fatty acids have melted. Each sample is analysed in 32 seconds. TDNMR is not the only instrumental method that can measure oil and fat content. However, it should not be confused with near-infrared spectroscopy and its associated disadvantages. Firstly, TDNMR penetrates the whole of the sample, not just on the surface, so measures a representative sample. This volume can be varied as required for the measurement. For example, larger sample sizes up to 100 mL may be required for inhomogeneous samples. Secondly, TDNMR calibrations are largely insensitive to physical properties, whereas near-infrared calibrations can be affected by particle size, color, and composition. As such, near-infrared calibrations require complicated models and hundreds of samples to ensure that the calibrations are valid. In contrast, TDNMR calibrations are simple and linear, which means that it's possible to measure samples outside of the calibrated range. Furthermore, it is often possible to calibrate using the pure oil for snack food or cocoa butter for chocolate spanning up to 100%. One of the key annoyances with near-infrared analysis is the lack of control over the calibration and results that it gives. There's no way of knowing whether the samples measured are represented in the calibration and results given are correct. In contrast, users have complete control over TDNMR calibrations as well as ownership. Furthermore, due to its accuracy, TDNMR can be used to validate the results provided by online near-infrared analysis. Fat, oil and grease, commonly known as fog, in wastewater can also be measured by TDNMR. It is important to measure its release from the factory into the sewer network, as it contributes to so-called fatbergs. It may also be illegal to release large quantities according to local legislation. One method involves passing defined volumes of wastewater through a glass fiber filter, which captures particulates as well as fog. Normally, solvent extraction is used to remove, then quantify the fog. Instead, the time-domain NMR method requires a batch of filters with fog extract to be dried, then conditioned at 40 degrees Celsius prior to the NMR analysis, which takes 5 minutes per sample. The drying time can be reduced if interested in non-volatile food oils and fats. The calibration samples are prepared using a multi-fat stock solution that consists of a variety of fats, oils and lubricants that may be analysed. Different aliquots are added to filter paper inside the vials. These are then dried, leaving filters with a range of fog contents, which are measured to create the calibration. Here are the results obtained from TD&MR using the previous calibration, compared against those from solvent extraction. It is important to note that there is a good correspondence between the two methods, especially at low concentrations. Large deviations between the two methods occur where extraction measures more than just the fog, for example, proteins from foods or glycerol from soap-based products, but also where reproducibility is poor due to inhomogeneous and difficult samples. It's important to note that in many cases the deviations are a result of the extraction technique and not the NMR. To conclude, time domain NMR provides fast, easy and accurate measurements throughout the food chain. Not only can we measure oil content of oilseeds to determine the crop value, but it may also be used to measure the efficiency of the crushing and oil content in the residue. Furthermore, TD&MR is used to measure the solid fat content at different temperatures to characterize the melting of the pure oil, fat, blends, or an emulsion such as margarine and butter. Droplet size can also be measured in margarines and spreads, as well as other food emulsions. Oil and fat content can be measured in a variety of foods, including, but not exclusively, potato and corn-based snacks, nuts, chocolate, confectionery, milk and other powders, as well as dry animal feed. It is also possible to measure fat content in other foods, specifically dairy and related products, where there are additional applications of interest. Finally, the same configuration that is used to measure oil and fat content in food can also be used to measure fat, oil and grease that has been filtered out of wastewater to ensure compliance with local legislation. At this point, I'll try to answer just a few of your questions. For those questions that I don't respond to now, I will answer in more detail in an email soon after the webinar. Furthermore, if you think of any questions afterwards, please contact us via our email address or website. Please also follow our LinkedIn showcase page, which provides updates on our latest news, including new applications, product information, and other webinars.
Окей. Отже, в нас зараз буде сесія питання-відповідь. Бачу в чаті, що вже є декілька питань. Kevin, we have several questions, and would you be so kind to answer them? I will read it in Ukrainian and then we'll translate it to you.
Okay.
Окей. Перше питання. Як саме... Це перше... Зараз, секундочку. Ага. Як зрозуміти, скільки потрібно зразків для визначення твердого жиру та при яких температурах їх кондиціонувати? Okay, first question. How to figure out how many samples are needed for solid fat content determination and at which temperatures they should be conditioned?
So in terms of number of samples, if you are, so you can either run the measurements by taking one sample, measuring at a temperature, and then moving that sample to another bath at a different temperature. So in that case, you'd probably only need one sample of each type of oil or whatever, but obviously that takes a long time. So the more common way to do it is to prepare one sample per temperature that you want to measure. And then you have multiple baths which you run in parallel, and then do the measurements after that. In terms of the temperatures you use, it's not really prescribed in any of the standard methods. So I guess most customers would probably take 5 or 6 different temperatures which span across the range of applications. So for example, from chilled temperature, say 5-10 degrees, up until about 40, when it has almost completely melted, or in some instances completely melted.
Okay, so it depends on melting point, yes, and like you always need to have one temperature that is related to melting point, and another temperature that is where when the fat is already melted, yes.
Yeah, it's more interesting before it melts.
Окей, thank you. Так, отже, translation, переклад. Кількість зразків, чим більше, тим краще, оскільки від цього залежить швидкість аналізу. Якщо буде тільки один зразок, то відповідно буде довше проходити аналіз. І також аналіз буде більш точніший, якщо у вас буде більше зразків. Це щодо кількості. Стосовно того, які температури потрібно обирати, і температури повинні бути різними для всіх зразків. Наприклад, якщо у вас для калібрування 4 зразка, то всі ці 4 зразка потрібно кондиціонувати при різних температурах. Як сказав Кевін, потрібно, щоб було 4-5 температур приблизно. Зазвичай так працюють наразі ті, хто використовують аналізатор для визначення загального місту твердого жиру. Перша температура має бути 5-10 градусів і обов'язково десь 40, це плюс-мінус кімнатна температура. Не кімнатна, перепрошую, це плюс-мінус температура, при якій плавляться жири, але також треба звертати увагу на те, яка у вашого жиру температура плавлення. Обов'язково має бути мінімальна температура 5-10, потім має бути температура, при якій починає плавитися жир, наприклад, там, в маргарині. І обов'язково має бути температура, яка відповідає тій температурі, при якій жир, що ви досліджуєте, повністю розплавлений. З нашого досвіду зазвичай це 10 градусів, потім це 40 градусів, 60, і якась ще проміжна між ними, може бути там 30, може бути 35, десь так, якщо використовуємо 4. І також, якщо 5, можна ще якусь там 40, 45, 50. Так. Окей, next question. Так, наступне питання. Як саме готуються калібрувальні стандарти для ФОК? Чи є якісь референсні стандарти? Це питання стосується стічних вод, визначення загального вмісту жирів, олій та мастил в стічних водах. Okay, Kevin, the next question is, how exactly are calibration standards prepared for fat, oil and grease content in wastewater? Are there any reference standards, like solutions or something like that?
So, as far as I'm aware, I don't know that there are any that exist, although I suspect there probably are some proficiency samples. But the good thing about time domain NMR is we can actually make up the standards manually. So we can effectively add different amounts of oil and then create the calibration that way. And in terms of what type of oil you use, I think it depends on what you're trying to measure. So, for example, a lot of the examples I gave in this presentation were generated in collaboration with a water company who deal with water and sewage. And so for that reason, we used a standard which included different types of oil and grease, which typically found in the sewage system. But we've also have customers who, for example, process oil seeds. So, for example, sunflower, and the main waste from their manufacture is sunflower oil, in which case you probably would use sunflower oil as your calibration oil, and you add different amounts of sunflower oil to the filters and then measure them by the NMR for the calibration.
Sorry. So mostly customers do their own samples using those oils and fats that they use in their production.
Yes, exactly.
And do you have some reference standard in the fork kit? As far as I know, as you have, for example, for solid fat content, you have this SAS.
Sure.
Do you have something like that for this application?
Unfortunately, not at the moment, but at least this kind of calibration can be created very, very easily, just using some real samples.
Okay, thank you. Translation. Отже, стосовно питання по калібрувальним стандартам для ФОК, референсних стандартів немає, і зазвичай калібрувальні стандарти готуються на основі тих речовин, тих як олій, жирів, які використовуються на виробництві. Наприклад, якщо це якесь виробництво соняшникової олії, то зразки готуються на основі цієї олії, калібрувальні саме стандарти. Є попередньо завантажена програма в програмному забезпеченні, відповідно до якого робиться це калібрування. І це все робить наш інженер, коли проводить інсталяцію. Наразі якихось референсних стандартів немає, але вони дуже легко готуються. Так. Окей, next question. Так, наступне питання в нас. Чи можна проводити аналіз шоколадних цукерок з наповнювачем на вміст жиру? So, Karen, the next question is it possible to perform analysis of filled chocolate sweets for fat content? I think we had a conversation once about this application. If it's okay to do analysis of not just chocolate, but some sweets with different fillings in chocolate. So that's the question.
Yeah. So I mean, for sure you can measure the total fat content in the sweet. If the question is, can we measure the different fats at the same time, I'm not sure, but maybe it is something we could try. So, for example, we can run application samples either here in the UK or at our applications lab in Germany. So, where we're not sure whether we can do something, we can certainly try to see if we can distinguish the different oils and fats. But so for sure, we can measure the total fat content in the filled chocolate sweets.
So it will be just total fat content, but not the particular fat, but like total amount of different fats.
Yeah, it's not proven, and also, obviously it depends on what the composition that they want to measure as well. So.
Окей, thank you. Отже, є деякі проблеми в визначенні аналізу шоколадних цукерок. Не можна визначити вміст конкретного жиру, оскільки шоколадні цукерки, якщо це з наповнювачем, то вони можуть мати різний склад. І якщо там будуть якісь горіхи, якась там нуга і так далі, вони всі складаються з різних жирів, тому щоб визначати якийсь конкретний склад жиру, потрібно повністю знати склад і калібрувати на основі повного жирного складу. От. Якщо це просто шоколад, тут проблеми немає, але якщо це шоколад з наповнювачем, то там буде дещо складніше калібрування. І якщо вас зацікавить така методика, то є можливість направити зразки на Oxford Instruments, і вони спробують зробити це на ЯМР-аналізаторі, надішлють результати, розкажуть, як вони саме це зробили, і тоді ви можете приймати рішення, чи підходить вам такий варіант, чи не підходить. Але при цьому загальний вміст жиру визначати можна, тобто всіх жирів, які містяться в цукерці. Okay, next question. При визначенні олійності соняшнику, яка максимальна вологість повинна бути для отримання об'єктивного результату? Okay, next question is about oil seeds analysis. And the question is, what is the maximum allowable moisture content to obtain an accurate and reliable results? What is the maximum moisture content? Is it 10?
Yes, that's correct. I mean, the ISO method specifies no more than 10% moisture. I mean, I think I've tried to measure above that, but there is some uncertainty whether the oil content measurements will be affected by that. So to be safe, less than 10%.
Okay, but I've seen, I don't know where it was. Maybe it's in Ukrainian official method, like ISO, but our own standard. And as far as I know, even 11% may be okay, but it's like can be okay, can be not okay. And we had a customer, they had moisture, maximum moisture, 10.5%, that was okay.
Yeah,
so,
I think
it's 10, yes?
Yeah, the ISO method states 10. I think I've measured up to maybe 13%, and it's been okay. I think largely, I mean, most of the time the seeds, I suspect, will have to be dried anyway to keep them microbiologically stable. So, and certainly I think the moisture content in most crops at a certain point will be less than 10%. But yeah, obviously if it's been freshly harvested, then it's likely that the moisture content will be too high. But yeah, as I say, to be safe, 10%, but potentially could be a little higher than that.
Окей, thank you. Отже, відповідь. Максимальна вологість взагалі по ISO і по ДСТУ має бути не більше, ніж 10%. Взагалі, теоретично може бути і 12, і 13. У нас був досвід, ми інсталювали ЯМР-спектрометр, аналізатор, і максимальний вміст вологи був 10,5%, то результати були точні, все було окей. Найкраще, щоб повністю відповідати офіційним методикам, щоб було не більше 10. Але практично воно працює і для більшого вмісту вологості. У нас в Україні, по тому, що ми вже інсталювали, то максимально було 11. І результати були окей. Тобто тут вже потрібно обирати, чи відповідати повністю методиці, чи можете ви відхилятися за якимись правилами вашої компанії, чи не можете. Має бути 10, але можна відхилятися, в принципі, від цього значення. Так. Наскільки я бачу, у нас більше питань немає. Okay, that was the last question. Thank you so much, Kevin, for this webinar, for this QA session. It's very important and good opportunity for our customers to have this opportunity to ask questions directly to someone from Oxford Instruments. So thank you so much. I hope we will see each other later. So have a great day.
Okay, thank you for inviting me. And as I said earlier, please, if you think of any questions afterwards, then you can contact us via AOT and I'll happily answer any questions you have.
Okay, thank you. I will translate this. Отже, Кевін, дуже всім дякую за те, що ви приєдналися, і нагадав ще раз, якщо у вас є питання, ви можете звертатися до АОТ, можете звертатися напряму до Оксфорда, він допоможе відповісти на ваші питання. Що ж, усім ще раз дякую за увагу. Будь ласка, звертайтеся, якщо у вас є питання. Підписуйтеся на наші соціальні мережі, слідкуйте на Ютубі. Також цей вебінар буде в записі, ви отримаєте його через емейл. А також він буде на нашому Ютуб-каналі. Всім дякую, гарного дня. Thank you, Kevin, again. So, have a great day and see you later. Bye-bye.
Okay, thank you. Goodbye.
Bye-bye.